Welcome back to ECE 320A. This is our review session for the final exam in 320A, and the final exam will be in 8 days, and it will be on a Wednesday. It's not a Tuesday or a Thursday. Make sure that you're aware of the date. The date is Wednesday the 18th, and the time is one of the final exam periods, which is the 2-hour time slot between 1 and 3. And I am planning to be in office hours Thursday on reading day from 4 until 5. And I have made available, I don't know if you've had a chance to look, but there are practice final exams on D2L. There is additional, and actually those finals, I don't show you the worked solution. I give you the solutions, but I don't show you how I arrived at those. So that's part of the benefit. But in the extra midterm practice exams, those questions do have worked solutions. Those, if you want, you can look at the no answer version and say, oh, I want to be able to solve this problem and try to work it, and then you can go and look at the solutions to that. But the idea behind the not working the final is for you to work through that and make sure you understand why those solutions are what they are. That being said, I think I posted a video of a final exam review session, so there's some worked problems, and we're going to do the same today. So you will see these final exam problems discussed, worked, or solutions. And the other thing is the TCEs. Please fill those out. I forgot to mention those maybe in the past. I'm not sure that I will be associated with that TCE, but that's okay. I want you to fill out what you are taking away from ECE 320A in the fall semester. Yes? So the question is, the question concerns you have a mix of faculty members that taught the class, and I think what I would suggest is the name attached to the TCE evaluation, that's who you fill it out for. Now, if you want, you can provide me with information in the comments. Maybe I can gain access to those or have Pratik give me those, but I think I don't think my name's going to be on there. So fill it out based on the instructor of record, which is Pratik, and then if you have additional comments about the two different instructors, put those in the comments of the TCE form. Is that clear? It is a little confusing, but I think that's a way to try to work it this semester. Any other questions before we proceed with working the final? Yes? What's going on with homework? I just checked on that, and Clarissa said she is finishing up her semester activities today, and so after that she's hoping to grade the 2 that you have submitted prior to me coming on. I just posted solutions to homework number 5, and I'm trying to get homework number 6 solutions, and I'll try to get those graded somehow. So those will be graded, homeworks 5 and 6, and you will have solutions to homeworks 5 and 6. You already have solutions to homework 5 today. I thought I posted it this morning. So see if that, and you might ingest a little caffeine before. I noticed it's 49 pages, the solution. but I'm kind of big with my writing, so it's not that. And I've provided extra information or worked additional parts to the problems, and I've worked them multiple ways. So it's not just one solution for one problem necessarily. Does that answer your question concerning homework? Any other questions? I'm going to try now to proceed with stepping through. Oh, and I guess I will try to follow this protocol that I've used in the past as far as what I'm allowing for the final exam, and I will allow a slide rule if you want to bring a slide rule. You'll have to clarify or clear that with no. But if you have one, I might come and look at it. I probably won't solve your problems with it for you, but I will maybe examine it to make sure I can remember how to use one. But those are the rules. I will allow you to bring in, and this is maybe a lot of information, but it's 4 pages front and back. So you now have 8 pages of notes that you can bring in to the final exam. Questions on the process of the final? Page 1. And it is multiple choice, but some answers are better than others, so there's partial credit, meaning one answer and only one answer is not necessarily the end-all for every problem. Some have multiple questions or answers that will give you some points versus the correct answer. Does that make sense? All right, so now we're doing a final value theorem problem with a transformed expression. And you might want to, in this case, look at pulling out the appropriate information. I would maybe factor the S out. We're wanting to know what's the final value of the time domain waveform x of t as t goes to infinity. If I now factor out the S, the pole at the origin, I can see that the linear factor in the denominator has a value of S that's negative. It's stable, so that's a good thing. I can now apply the final value theorem. I'm now looking at S x of S, and I'm looking at the limit as S goes to 0 of that expression. The S in the numerator of my S x of S cancels the pole at the origin, and I now simply let S go to 0 with what's left, and I end up with 2 over 10, or 1/5. If you don't remember how to do the final value theorem, you could inverse Laplace transform that and let t go to infinity and find the same answer. Problem 2. And here you'll want to make sure you're reading the question carefully. If y of t is the convolution of an impulse response h of t and an input waveform x of t, where h of t is actually given as a transfer function, it's the Laplace transform of the impulse little h of t, I now have capital H of S, and here is the time domain waveform for the input x of t, which is 3e to the minus t. I'm exciting a system that's described by this transfer function h of s. I'm exciting that with an exponential. And I want to know what's the structure of y of t. That means if you did the part, and I would recommend setting up the partial fraction expansion, but just don't solve for any of the coefficients. Don't solve for any of the residues. Don't find A, B, C, and D. You can, but it's going to cost you time, which you could spend elsewhere. I'm just wanting the structure, and the structure is concerned with the modes. Where are my poles of my transfer function, h of s, and where are the poles associated with my input waveform? In this particular case, hopefully you can see that if I looked at capital X of s, what would that look like if I Laplace transformed little x of t? It's scaled by 3, and now the Laplace transform of e to the minus t isn't that 1 over s plus 1? Now you have that, and you have this third order denominator, and you might want to then look at the roots of that quadratic and say, okay, is this giving me real roots? And those roots could be real and unequal or real and equal for overdamped and critically damped. Or is it giving me complex conjugate roots? And were you told how to examine a quadratic polynomial and determine immediately if its roots are in the left half plane? What do you need to know if you just look at a generic quadratic and you can by inspection say, oh, I know all of its roots are in the left half plane? You can show, have you looked at the Routh-Hurwitz test? Maybe not. So that's basically what I'm telling you here. Well, for a quadratic, you can simply look at, are the constant term and the linear term present? In this case, there's an 8 and a 4. They are present. And are they positive? So in other classes, I would say present and positive for these coefficients. You have 8 and 4 with the s squared there, and now you've factored out the leading coefficient or made it monic or made it 1. If those two coefficients are present and positive, you're assured of those roots being in the left half plane. And you could then convince yourself via some examples of finding, if you just did the quadratic formula, it's minus b, and now it's minus 4, and depending on what the radical gives you, and in this case, it's not going to bump you into the right half plane when those two coefficients are present and positive. But if we now looked at this, we could say, oh, this is, let's see, s plus 2 quantity squared would produce the s squared plus 4s, and it would also give me a 4. And now I need to add in another 4, or 2 squared. And this structure gives me the mode or the structure of my time domain response. I know that I have an exponential damping of sigma, actually minus sigma, and I know my damped frequency, omega sub d, is 2. So in this case, this factor in the denominator immediately tells me I'm dealing with something like that. E to the minus 2t, cosine of 2t, and I don't know because I would have to determine a, b, c, and d, or the coefficients, the partial fraction expansion coefficients associated with that term in order to find theta. And I'm not interested in the precise value of theta. I now know that it's either c or d. And I now look and say, oh, this one will give rise to what structure? This now gives me an e to the minus 4t, and I already know what this factor gives me. It gives me an e to the minus t. This now is there, and this one is there. And now we can say, oh, by some analysis, I've determined that the structure associated with that particular problem is going to give rise to y of t having that structure. Yes? Which ones do they correspond to? That's a good question because this is a poor example because of the 2 and the 2. This 2 goes there, and this is the omega d. So if this was now s plus a squared plus b squared, then this would give rise to an e to the minus at cosine bt plus theta. Does that help? And that's really what you're doing when you have these complex conjugate roots. You would have a cosine term and a sine term, and we're just putting them together into a cosine term. So if you have a exponentially damped cosine of 2t, and the damping is e to the minus something, well, if you now have a sine term of 2t with the same exponential damping, you can put those two together in either a cosine or a sine form with a phase shift. Here I've said, oh, I'm going to combine those into a cosine and have the phase shift represented as theta. Did that answer your question? So I could have said something like the following. One of the answers that would be okay would be an a e to the minus t plus a b e to the minus 4t plus a c e to the minus 2t sine 2t plus a d e to the minus 2t cosine of 2t. That likewise would be a valid, correct answer. And I've simply combined the exponentially damped sine and the exponentially damped cosine into a cosine. Because it's easier to sort of draw one instead of drawing two and then adding them up. But that's essentially what you're doing when you consolidate 2 into 1. Other questions on 2? Problem 2. Problem 3. I know some of you maybe didn't know what I was talking about, and I didn't bring this. So it says, this butter be worth some extra credit. How do I award extra credit if there's no name? Yeah, I'm sure I'll have a lot of volunteers now, but here's question 3, and it does deal with Butterworth filters. It now says the following. It says if a filter is being designed from a normalized low pass, and we want to now create a filter that has these characteristics or properties. We want it to have a Butterworth characteristic. Do you know what that means now? What do you see when I say a Butterworth characteristic? You can see many different things. Some of you are now saying, oh, flat. What's the pole pattern? Do you see the pole pattern? It's now distributed around the unit circle so that it, what? Subdivides your unit circle uniformly, and it will rotate depending on whether it's even or odd. You'll always have a pole at -1 if you have an odd ordered filter. Otherwise, you're splitting the negative real axis with the overall angle, and you're going up half of that angle and down half of that angle with an even ordered filter. You want a Butterworth characteristic, and some of these may be red herrings. Some of these statements may not be critical to the answer. A low-pass filter with a bandwidth of 500 hertz, and pay attention to hertz versus radians per second, the normalized Butterworth is using what frequency? It has units of radians per second, and it's 1. So you need to make sure if your question is being asked, is it in hertz, is it in radians per second? A high-frequency magnitude roll-off of minus 40 dB per decade, and a low-frequency phase of 0 degrees. And now it says, what statement is true about the filter order and the frequency scaling factor? A low-frequency phase of 0 degrees. Does that give you any useful information? We're saying we're starting with a normalized low-pass filter. For any order, we're going to have a low-frequency phase of 0 degrees, so we don't need to worry about that. And the Butterworth, okay, so what? It's tasty, but it's not really giving us the information we need. We need to now focus on a bandwidth of 500 hertz and the other property, which is a high-frequency magnitude roll-off. And I could say something about the phase. I could say, oh, the phase at high frequency equals a certain degree value. What does number 3 tell us? It now says we have a second-order filter. So now we're dealing with A and B. And property 2 says, oh, we want a cutoff of 500 hertz, but we know that our normalized filter is omega 1 equal to 1 radian per second. We now need to convert this to radians per second. So now we have 1,000 pi. And so omega 2 over omega 1 is now 1,000 pi over 1, 3.14159. So there is our frequency scaling factor. And that's now B. The correct answer. You might get a little credit for saying it's second order. At least you got some of it right. And you went too fast and didn't pay attention to the distinction between frequency in hertz and frequency in radians per second. But if I now said, oh, I have a filter that right now has a bandwidth of 200 hertz, and I want it to actually have a bandwidth of 1,000 hertz, you don't have to convert either of those to radians per second because you're just worried about the ratio. Omega 2 over omega 1 is the same as F2 over F1. It's just when they have different units that you have to worry about it. The 2 pi's cancel. And they don't cancel if they have different units. Yes. Pardon? So why is the cutoff frequency at minus 3 dB? We now have this. This is our straight line approximation. And we are actually, in reality, the cutoff frequency is that location, and we're in fact minus 3 dB down from this low frequency gain value. And you can see that, let's say that we just had a first order, and it's true for all orders, but now if we were looking at this first order, that's what we have in terms of its magnitude. And we want to know 20 log base 10 of that. And what is the break frequency for this? We now find the pole, and that now tells us the break frequency. Our break frequency, omega c, is 1. If we now evaluate this at that value, you now have 20 log base 10 of 1 over the magnitude of 1 plus j. And what's the magnitude of 1 plus j or j plus 1? Real part squared plus imaginary part squared, square rooted. So at the cutoff frequency, or at the break frequency, we're really looking at that. And you would ask the question, wouldn't you? So this is now what? This is now 2 raised to the minus 1/2. You're always interested in logs, I told you. So now what happens with the properties of logs? That exponent can be brought out front. We now have 20 times a minus 1/2 log of 2. And this could be on your 4 sheets of notes, the log of 2. And this is minus 10. So now you have minus 3 dB is the actual value of the magnitude plot at the cutoff frequency. Our straight line approximation just neglects that. We just say I'm flat until the break frequency and then I start sloping. In MATLAB, in reality, the actual will be flat, but it's starting to bend and it goes through minus 3 dB at the break frequency or at the cutoff frequency, or that determines our bandwidth. Questions on, did that answer your question on cutoff? Did I ask the cutoff? I didn't ask for the cutoff frequency or state that in that problem. Problem 4. We now have a bandpass filter, which you don't really need to know necessarily, but you're given the fact that the center frequency of the given filter is 8,000 radians per second. We now know where the center frequency is. If we want to change the center frequency to 1,000 radians per second with a resistor value equal to 1,000 ohms, what will be the resulting value for the inductor L? This is now dealing with magnitude and frequency scaling, that concept. We now need to find what's our magnitude scaling factor, what's our frequency scaling factor, and use that to determine our new inductor. When the original filter that had a center frequency of 8,000 had an R equal to 1875, a C equal to 100 nanofarads, and an L equal to 156 millihenry. Where do we start? We need to find two. We need to find K sub M and K sub F. And if we can find those, then we know L sub 2. The new inductor value is magnitude scaled divided by the frequency scaled, our original L. That's where we're going. We want to use that expression. We want to know what's our new inductor's value if we start originally with 0.156 Henry. We need to find a K sub M and a K sub F, then just multiply that by the 0.156 to obtain the new inductor in our scaled circuit. What's our frequency scaling factor? The new over the old. What's the new? We want to change the center frequency. Actually, we're trying to scale it down from 8,000. We want to go to 1,000 from 8,000. Or K sub F is now 1/8. Or 0.125. K sub M. How do we find that? Are we changing any of these R's, L's, or C's, and are we given both values before and after the change? The original resistor we are given, that's 1875, and the one that we want in our new circuit is a 1K resistor. So that now says that R2 over R1, we want a new one to be 1,000, and now I can see where maybe you're going to get confused onto which one is where, but I think the units will help you with that, so maybe it's poorly designed for a discussion question for getting ready for the exam. That 1,000 is 1,000 ohms. R1 was 1875. You plug all of those in, scale, use that to scale this L1, which is the, and you end up getting that value. Meaning you're plugging it into this formula. You know K sub M is less than 1. You know K sub F is even smaller than 1, and now you're hitting that with 0.156. Problem 5. And here you want to make sure you're not going so fast that you go reading something into it. This is now a single phase power question, not a three-phase. So you don't need to worry about positive and negative phase sequence. You don't need to worry about phase voltage and line voltage, etc. This is single phase. That's going to give you the same information. A single phase system has two loads connected in parallel. We now have L1 and L2, and I would suggest you make sketches. You have these two loads. Load 1 absorbs 500 volt amperes with a power factor of 0.6 leading. Load 2 absorbs 500 VARs, not volt amperes, but VARs, at a power factor of 0.8 lagging. And you're asked to find the RMS current magnitude supplying the two load combination. And you're also told that the line voltage is 500 volts. What can we say regarding load 1? Or what can we compute? What are we given? And now, are we given apparent power? Are we given real power? Are we given reactive power? What are we given with load 1? And this is all based on the units. The units of apparent power is volt amperes. And that's the units on complex power, volt amperes. Yes?
If we're just given VA, do we assume that there's no watts that are observed by that load?
So now, since we are given only VA, do we assume there's no watts? No. So all we know, what? So the VAR, if we have VAR, do we assume that we only have VARs? What tells you that you can't make that assumption? The power factor. The power factor says, oh, if you had a power factor of what? 0, then you would have all reactive power. But since we have a power factor and lagging and leading, lagging says what kind of a load does that represent? Inductive or capacitive? Lagging is associated with an inductive load, and that's a positive Q. So now if you're drawing a diagram, that 1000 VA gives you your hypotenuse. This is why I'm allowing you all of these drawing instruments. Protractor, straight edge, you can bring those to the final exam, and you should use them. You now know that you're at 1000 volt amperes and 0.6 leading. That tells you your angle, and that one is negative. So for load 1, we are actually told the magnitude of S1 is 1000. The power factor is now 0.6 leading. And now with the power factor, we can actually find what is our real power. That is S1 cosine of theta, but cosine of theta is actually just the power factor. So this is now 1000 times 0.6, or it's now 600 watts. And you could now sketch your triangle. The hypotenuse is 1000 and the real part is 600. And now you can figure out what the imaginary part is, or you can go ahead and compute that. You can say, oh, the angle, theta 1 is now minus, since it's leading, inverse cosine of whatever it was, 0.6. And now you could say, oh, now I know what Q1 is. It's S1 sine of theta 1. There's S1. S1 is now 600 minus J 800. Load 2, we're given information that we'll probably be able to obtain everything from, but it's in a different form. Now we're told what Q2 is. Not S1, not P1, or not S2 or P2, but Q2. And we're told what the angle is, indirectly through the power factor. We now know then from load 2 that Q2, and what's the sign of Q2? Lagging says it's positive, so now we have plus 500. Power factor was 0.8 lagging. Theta 2 is then the inverse cosine of 0.8, or that's now 36.87. And if we go back and we say, oh, Q2 is now the projection of the apparent power on the vertical axis, and theta sub 2 is the 36.87, so now we can solve for S2 to end up with 833.3. That's the hypotenuse of the second load. And P2 we can use all the information that we now have, and this is now or now we have all the information about load 1 and load 2, so what? Well, now we know what the total load is here, and we can complex, and we can use that because we now know that S total is V I star. And in fact, we just need to find the magnitude of I, so we could take the magnitude of both sides and solve for I. And S total I don't know that I showed any of that, but it's now 1267 minus J300. You do need to make sure you do it algebraically. This is now volt amperes. We can find the magnitude of that. Divide that by the magnitude of our voltage, which was 500, and that's now the magnitude of our current. And the voltage was in RMS, the current will be in RMS. Question 6. Find the total complex power absorbed by the RL load when I sub G is 20 cosine of 40t, R is 10 ohms, and L is 0.125 henries. What's the most common mistake made on this question? Is this single what? So you could misread the current and think it's a voltage source. It's actually a current source, but what typically people do is they forget that that's the maximum, the amplitude, and all of our power formulas are usually used with RMS values or units. Meaning, if this is now, if we want this in RMS, we now take I sub G max, or amplitude, and divide it by the square root of 2. And what's our total complex power? if I simply call this Z. This is V load, I load star, where those are both using units of RMS, or in RMS units. We can use Ohm's law to get rid of the V. So this is now Z load I times I star, or this is now Z load magnitude of I squared. Can you give me Z? R plus j omega L. R was given to be 10 ohms. What was omega? That was 40. And L, or 1/8 of 40. So this is now 10 plus J5. That's Z load. And what is I sub G? So now I sub G in RMS is 20 over the square root of 2. Which now allows us to say, oh, S total is now 10 plus J5 times 20 over the square root of 2 squared. And hopefully that's one of the answers. Bode plot. Straight line Bode plot for this transfer function has a magnitude slope at high frequencies equal to S1 and a phase slope equal to P1 between omega equals 0.2 and omega equal to 0.8. I'm really just looking for values for S1, which will be a slope, and P1, which is also going to be a slope of my phase curve. So you're really going to have to look at this transfer function and sketch both its magnitude and its phase, but the high frequency, you don't have to do much with the magnitude to worry about the high frequency. How many zeros do you have? Finite zeros. You have 2. How many poles do you have? You have 3. So you have a pole 0 excess of 1. You have one more pole than 0. So at the end of the line, at the high frequency, effectively you have one pole. Is that making sense? After all things have broken, You've gone through all the break frequencies. You've had 2 zeros break and 3 poles break. At a high enough frequency, you're really just sloping as if you had a single pole. And that now gives you S1. What's S1? Minus 20. And boy, you're done. You don't even have to... There's no more options. But maybe it could be none of the above, so you better check. So now you want to look and say, okay, where is everything breaking? And we're supposed to be looking between 0.2 and 0.8. So what actually happens in those intervals? We now are 10 to the minus 2, 10 to the minus 1, 10 to the 0. Does this influence our phase slope, that pole at the origin? No, that contributes a flat minus 90 degrees. That's not giving us any slope. Do we have any poles that break in their phase before 0.2? Do you see that we have that factor? And what's its phase going to be? Where does the phase begin contributing slope? It's going to be at a decade below that break frequency. The break frequency is 10 to the minus 1 or 0.1. So at a decade before, it's going to start introducing its slope change in phase. Here is our phase plot. And which way do I go with that factor? It's downstairs. I'm going down, and it's going to be split over 2 decades. It now gives me that kind of a picture. And this is now minus 90 degrees. That's this. Do I have anything else active in phase between 0.2 and 0.8? That's all that I have for poles that give me slope, because the pole at 100 doesn't introduce phase until 10. But now I look at my zeros, and I have 2, and they're repeated. And they are breaking at 1. So a decade before that is when they start. They are going to start contributing phase at 0.1. So now I'm looking at those two, and they will spread that over a 2-decade interval on up to 10, and they are now going up to plus 180 degrees. What's this slope? I go from 0 to 180 over 2 decades. So 180 divided by 2, this is now plus 90 degrees per decade. What is this pole slope? It's minus 90 over 2 decades. It's now minus 90 divided by 2, or more, minus 45 degrees per decade. What's my net slope? I just algebraically combine those slopes. I'm going up between 0.2 and 0.8. That's now in this sweet spot right here. Well, it's not quite that. It's not quite to 1, but you get the idea. And what's my slope? I meant to there. Is it 0 degrees? So is it this answer? So I have plus 90 minus 45. The algebraic sum is plus 45. So in fact, A is the correct answer. Do you want to see some transfer functions, or do you want to do some three-phase power or convolution? Question?
For the magnitude plot, does each pole contribute negative 20 decibels per decade no matter what?
So,
For example, if it was like S plus 1000, that's still being negative 20.
so now the question concerns each of these linear factors. How much magnitude slope do they contribute? And it doesn't depend on the break frequency. The break frequency just influences where they initiate that slope. But a linear factor is going to contribute minus 20 dB per decade. And the pole at the origin, it never breaks. It's always contributing minus 20 dB per decade. But those other... I'm playing hockey down here with the gravel on the floor, sorry. You probably can't hear that or see that, but you're wondering what I'm doing. Heard something I was stepping on, so it was giving me a slope change. But the one at 0.1 gives us minus 20. The one at 100 gives us minus 20. So when all of those poles are active, if we didn't have any zeros, we would have a slope of minus 60 dB per decade due to those poles at high frequency. But since we have those two zeros, they contribute their slopes and they take away 40 dB per decade. And the net is then minus 20 dB per decade. Yes? Will we ever have an angle? Well, the question was, will it ever have a slope change different than plus or minus 45 degrees per decade? Yes, if you have repeated factors, which we do. This zero is now repeated. We have two zeros at s plus 1. I'm sorry, two s plus 1 factors, which gives us two zeros at s equal to minus 1. Each of those contribute their own plus 45 degree per decade. Combined, they give us plus 90 degrees per decade. But if you simply have a linear factor, they will be giving you plus or minus 45 degrees per decade. Spread over 2 decades, this is our straight line approximation, and that 2 decade is centered over the break. So you start at a break and you go down a decade, that's where you start the slope. You go up a decade, that's where you stop the slope. But it continues to provide minus 90 degrees or plus 90 degrees of phase beyond that decade above its break. Yes?
Like in the bottom, instead of having like s plus a constant, you have like s plus something, but the constant was like both real and complex, or real and imaginary.
So now I think the question is something, what if you had s plus, well, let's say this. That actually has complex roots. This is now at minus 1 plus and minus j5. I don't know why I picked such an ugly value. But we will actually, well, I didn't want to go into that level of detail. But what we would do in this class is we simply say, oh, let's just look at that. And we'll just treat that. That's how far away we are from the origin, squared. That's our natural frequency squared. We are in a picture. We are at minus 1 plus and minus j5. So we have these two, let's say, poles. our distance away is that length. What I typically tell classes when we're first doing this, so that we don't have to worry about where that pole is relative to the imaginary axis or the real axis, I simply say, you know what? These are just straight line approximations. This is crude, but let's just rotate that through its circle. That's supposed to be a circle. And this point, I just put 2 poles there, and then I just go with that. But effectively, it has a little bit more exciting behavior, but the way I'm doing it, I would just go to here, which is now the critical frequency, which is what I'm saying this is. That's the omega c. And now how fast do I slope down? I had this pole there and I had this pole there, so I now have 2 poles that I have active. This is now but depending on how close that pole is to the imaginary axis, it gives us the real has some ringing. So the closer we get to the that's ugly, but if it was right at the sweet spot at 45, then you're going to have something that looks more like our normal approximation. And if they were right there and real, we would be 6 dB down. We are just approximating that elaborate behavior with just saying, okay, let's forget that they're complex. Let's just treat them as if they are 2 real equal poles. Their distance is determined by their natural frequency, the distance they are away from the origin. Yes? Can I what? Can I have half poles? No, we're not going to allow half factors. You're saying, do we have something like this? No, we're going to have, we're not having fractional powers in our numerator or denominator, which is what that would result in. So we now have inductors and capacitors. They are giving us integer values of S. So we have polynomials in powers of S. Do you want to find a transfer function, or do you want to do something else? Transfer function. So now we want to find the transfer function of this circuit, which now we simply need to remember that for an R in the S domain, that goes to R. An L, its impedance is SL, and a C, now that's 1 over SC. Or now if we redraw this circuit in the S domain, there's V1 as a function of S. Here is R. That just comes over as R. We had 1 over SC, and C was 1. That gets nice and clean. And L being 1, this is SL, that's S. That is now our S domain circuit, and we now want to find V sub 0 in terms of V sub 1, so that we can, in fact, create this ratio, which is our transfer function. And now pick your favorite strategy for analyzing this. We could say, oh, this is a voltage divider, if we wanted to, where this parallel combination of impedances is dividing V1 into V0. If we now looked at this, we now have 1 over S in parallel with S. Or that's now S times 1 over S plus 1 over S. Or clearing the fractions, upstairs we have S over S, and downstairs we have S squared plus 1 over S, getting a common denominator in numerator and denominator. Those denominators are common, they cancel, and we're left with the impedance of that inductor capacitor look like S over S squared plus 1. And if we call that impedance Z sub 2, then V sub 0 is now Z sub 2 over Z1 plus Z sub 2 V sub 1. This is just now a voltage divider. And if we want the transfer function, we can divide both sides by V1. And whatever Z sub 2 was, that was S over S squared plus 1 over Z1 was just R. There's our transfer function H of S. You could do node voltage analysis and have V sub 0 as your node voltage and solve for V0. It's whichever way you feel more comfortable writing those equations. Now we want a valid equation for the following circuit. And we need to account for initial conditions. The initial conditions do what? Or how would you probably, just looking at the options A through D, what kind of analysis would you focus on in terms of how do I want to find this equation? So now we're probably going to do a mesh analysis or KVL because the impedances are scaling I sub L. So that's really not giving you any unique information. The left-hand side is the same, and that better be the impedance of the inductor, S times 1, plus the impedance of the capacitor, that's 1 over SC, that's 1 over S2, plus the resistor, which is 4. So everything inside the parentheses scaling the current is the total impedance seen in that series connection. The difference is all relative to the initial conditions and this source. And in fact, the source, the only thing different there is the sign, but that will allow you to eliminate 2 of the answers. If we go KVLing around that mesh, we would have minus V sub G plus all of that I sub L is equal to 0. But we need to account for the initial conditions, but I'm just now quickly saying, can we eliminate some of those? And what is V sub G? There's V, that's V sub G. So now we're looking to say, oh, we need this. Oh, I guess we threw out 1, didn't we? Oh well, at least we don't have to worry about D. But now we have to figure out how the initial conditions come into play, and that's based on Eli and ice, or the inductor. And the capacitor. If we're doing the series combination, now the capacitor, and just plug those in where the inductor and capacitor are with the appropriate initial conditions, and you should be able to determine that, in fact, the correct answer is B. So the signs are influenced by how you incorporate initial conditions into these inductor or capacitor circuit elements in a given circuit. Meaning, the resulting equation or circuit will be this. There's V sub G, here's the inductor, then you have the inductor's initial condition, which will end up just being 2. You have the capacitor and its initial condition, and then you have the resistor. And you now end up with minus Vg plus S plus 1 over 2S plus 4 times I minus 2 plus 4 over S is equal to 0. You push all of those forcing functions, which are the source and the initial conditions, to the right-hand side, and you end up with B being the answer. Are you following what I'm suggesting the strategy is for solving that? You incorporate the initial conditions due to the inductor and capacitor, and now you look at what was asked and you say, oh, they're writing a mesh equation or a KVL equation. Let me do that, and that means I need to incorporate my initial conditions as if I'm writing mesh equations, which says I need to incorporate those as series voltage sources. Yes? How do you determine the sign on the initial condition? That's all based on Eli and ice. I thought I went through that. Did I? Earlier in a lecture? I thought I did. So if you look at this, V sub L of t is equal to L di sub L dt, and Laplace transform that and account for the Laplace transform of a derivative, you end up with V sub L of S is equal to L, and this now is S I sub L minus I sub L of 0 minus. You put all of that together and you now see that, oh, here's my impedance of the inductor, and here is my initial condition piece. This piece is right there. That's how those come into play. And now if you have that in your circuit, you immediately just plop down that initial condition and impedance for your inductor and capacitor. If you have 0 initial conditions, then those voltage sources, how do you zero out a voltage source? You just short it out. So it doesn't kill your analysis, it just makes it easier. Wow, I still have a minute. How about we look at this? Can I talk through the convolution? Quick. How would you solve this? Now I'm asking for the value of the output at one instant of time. Have we talked about that before? Which one would you want to flip and slide? H. Good. So now that only has one thing. We flip it and slide it. We now are flipping and sliding that, and if I changed this to lambda and this is lambda, now I have this is what? T minus 3, T minus 7, and this is 4 for an amplitude. I slide that over and stop when T is equal to 9. Do you see that that's actually going to put it right here at 6? And it's going to go here, and this is going to be at 2. This is T minus 3 when T is equal to 9. So now what am I doing? Now I'm simply multiplying these two waveforms together when they are overlapping. I have a unit width on the left and a unit width on the right, and I have 2 times 4, or 8 times 1. 8 height, 1 width, 8 times 1. The one on the right is width of 1 still, 5 to 6. Height of 1 times 4, that's 4. 8 plus 4 is 12. My answer for y of 9 is 12. Convolution done. Thank you. I will see you in 8 days.
Hello, sir. Sorry I was a bit late to the class. I'm pretty sure you went over it, but I just wanted to confirm these are the chapters coming in the final.
I would have, yes, probably 10, 11, 12, 13, 14, 15, and Appendix E.
Yeah, it's in this one.
Mm-hmm.
Thank you.
I'll have to